Hello guys, we are back with another question from analysis, NBHM 2019, 2.5 question. So we are given with a finite interval, a function f is said to be bounded variation if there exists a real number L which is positive, such that whenever we are given with a partition, so AB is an interval, AB are both finite real numbers. So whenever we are given with a partition, then when we consider f of xi minus f of xi minus 1 sum, what we do is basically this. This is suppose a b x1 x2 dot dot dot. So what we do in each, suppose the function is like this. So for each interval, what we do, we take difference between the, let's suppose x1 x2. The first one, what we do, we take the difference between these two values, right? And then for this one, we take the difference between these two values, the functional values. And if the sum turns out to be less than L, and this should happen for all partitions, then we say that it is a function of bounded variation. Okay, so what we are asked to in this particular question, this definition is given, then we are asked to say whether some particular type of functions are bounded variation or not. Okay, so let's first consider f is a monotonic. So we are asked if it is a bounded variation or not. So let's consider this sum. Okay, so what will be this? F of x0 minus f of x1, f of x n minus f of x n minus 1, right? Now let's suppose I'm considering f is decreasing. Okay, f is decreasing, monotonically decreasing. We can similarly do for monotonically increasing case. So if f is decreasing, then f of x0 is greater minus, this is positive, right? So what would happen, this sum will be f of x0 minus f of x1, right? Then similarly f of x2 minus f of x1 mod, that will be basically f of x2 minus f of x1, right? Dot 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 up to each modulus will be the same, because that each term inside the modulus is positive, greater than equal, non-negative basically. So f of xn minus, so what happens is these terms cancel out, and what we get ending up with f of x0 minus fxn, right? Now f of x0 is basically a, this is so fb minus fa, right? So this we can take as L, sorry, this is fa and fb, right? So this we can take as L. So this is so if f is monotonically decreasing, this monotonically decreasing, we have L is equal to fa minus fb, and if f is monotonically increasing, then L we can take to be fb minus fa, right? So okay, I think here it should be f of x1 minus f of x2, because f of x1 minus f of x2, this is f1, and the last term will be what? Okay, so this is fine, but then now on this one, if you consider f of xn minus, this will be f of xn minus 1 minus f of xn, right? Since f is decreasing, right, monotonically decreasing, so f of x minus 1 xn minus 1 is greater than f of xn, right? So there's some just, so the cancellation will be like this, consecutive wise, and then this f of x2 minus f of x3, so consecutively these will cancel out. For monotonically increasing, L will be similarly fb minus fa. Okay, so now what we do, we consider, so option A is true. Okay, so now let's consider the option C. This is very easy, because f and g are given to be bounded variation. So what we have, there exists some L such that whenever we are given, let's suppose we are given with a partition P which is x0 x1 up to xn. So since f is a bounded variation, there exists L positive, such that summation I equal to 1 to n fxi minus fxi minus 1 mod, this is less than equal to L, right? And then again for this particular partition, since G is a bounded variation, there exists some m positive, right? So that right. So now we want to see whether f plus g is an boundary variation or not. Of course, the obvious choice is L plus m. So what we consider is this. Consider this for I equal to say 0, 1, 2, 3 up to n. Okay. So this is basically now using triangle inequality we have right. Now take summation from I equal to 0 to n and we have our result. This will be summation I equal to 0 to n, I equal to 0 to n. This is okay, sorry, I equal to 1 to n, then this is less than m, L, this is m, right? So again C, option C is true. Now we consider the option B, right? So f is this symbol means f is continuously differentiable, right? So what we have is that means f prime is continuous. Now f prime this okay right. Okay, so now f is now f prime, this we can define on closed AB to R. This is a compact set, right? So the image of f prime AB, this I am denoting as image of f prime AB, this is compact, right? This is compact in R. That means, and in real numbers it is bounded, closed and bounded. That means in particular f prime x is mod is less than equal to m for some m positive, right? And for all x in AB. Now what we will do, I think this is clear, up to this is clear. Then what we do is basically we apply our usual mean value theorem on the intervals xi minus 1 to xi. Okay, so apply mean value theorem on xi minus 1 to xi. Okay, so what you get is basically there is some zeta I belonging to this particular interval, such that what happens, oh sorry, this will be inside open, so that what happens, f of xi minus f of xi minus 1, this equals to f prime zeta I xi minus 1, right? Now take the modulus and sum over 1 to n, sum over I equal to 1 to n, right? Now each of these zeta is, these belong to AB, so these are bounded by m, so this each of them is bounded by m, so we can write this as summation less than equal to summation I equal to 1 to n m xi minus 1 modulus. Now m comes out minus 1, right? But we are not done yet, because we have to show a upper bound, but this is simple, right? Because when you sum over it, what you got, what do you get is x1 minus x0, right, plus x2 minus x1 dot 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 xn minus 1. Okay, so basically what happens, this cancels out, so what we get is xn minus x0, that is b minus a. Right. So what the overall bound what we get is basically m times b minus a, right? So this we can take as sum L, which is positive, and then we can then we get what that f is as a bounded variation, right? So then option B is also true. So guys, if you like our videos, please subscribe to our channel, and we'll be uploading more and more videos like this. If you find this content helpful, please do share these things with your friends so that they will be helpful, and it will also motivate us to do more videos like this. Thank you.